Good morning, students. In today's class, we will be studying about the relationships which connect the Young's modulus, bulk modulus, and modulus of rigidity and the Poisson's ratio. All these relationships, we are going to connect it together by a equation. Young's modulus Y, bulk modulus K, modulus of rigidity eta, and the Poisson's ratio sigma. We are going to connect it with the equation. Okay. In the very second video, okay, of mine, you must have seen the relationships which connect the Young's modulus, bulk modulus, and the Poisson's ratio. Okay, these three, okay, has been studied: Y, K, and sigma. Okay? And this was discussed using a Q, and when it is compressed on all the sides. Okay, how the bulk modulus value changed, okay, and what is the change in the volume we found out, and then subtracted it from the original volume, and then using the bulk modulus formula, volumetric stress by volumetric strain, we put it up into the equation form, and then we got one equation. Do you remember the equation that we got? It was, and especially when we introduce the term alpha, we all know that alpha is nothing but when a stress is given to your body, there will be elongation on one side, okay, and there will be a compression on the other side, isn't it? So let us consider that alpha be the linear or the tangential. Okay, let alpha be the linear or the tangential strain produced per unit stress. Okay, if alpha is a linear strain produced per unit stress, and if beta, okay, this produces, if there is any stress given to your body, okay, the body may undergo a linear strain with per unit stress on one side, and simultaneously there will be a compression. Okay, so there will be a compressive force which will try to reduce the maybe the volume or the length. Okay, so B in terms of length, if we take, alpha be the elongation. Okay, so this is an elongation factor. In terms of, suppose you consider a wire, and if you are giving a stress on one side, there will be elongation which is in the form of strain, change in the length per unit stress, and at the same time on the other perpendicular direction there will be a compression. Okay, so beta will be the lateral strain, okay, per unit stress. Elongation and compression takes place on the perpendicular direction. Okay, so having these two factors, now we will go back to the equation that we derived with respect to the Young's modulus, bulk modulus, and the Poisson's ratio. Okay, so do you remember this equation that we got it as P is equal to 1 by, with respect to alpha and beta, I'm giving the equation. I'm not giving the final equation. I'm giving the equation with respect to the linear strain, and with the lateral strain, it is 3 into alpha minus 2 beta. Okay, so let's take this as equation number 1. Okay, this is there in your book also. Okay, and also similarly, we found another equation from here. Okay, when we divide the numerator and the denominator, if you remember, when we divided this equation on the numerator and the denominator with alpha, okay, alpha divided by alpha, 2 beta by alpha, okay, this will become, this factor is equivalent to y divided by 3 into 1 minus, this beta minus alpha is, beta divided by alpha is nothing but Poisson's ratio sigma. Okay, so we got K as y by 3 into 1 minus sigma. Okay, got these two equations. in the very first class when I dealt with y, eta, yk and sigma. Okay. So this two equation, I'm writing it one more time. Okay. And similarly, okay, we derived an equation for modulus of rigidity in another video. Okay. Do you remember that body is being given a shear stress along this side, okay, and there will be an elongation along the length, and then there will be a compression along the other side, A, B, C, D. No? B is elongated to B dash, A was elongated to A dash. Do you remember this figure, this derivation that we derived? Okay, so in the diagonal there is an elongation, okay, and elongation was taken. The change in the elongation, how much the length BB dash was sheared in terms of angle V to BB dash is equal to cos 45. Like this we derived, isn't it? And that from that relationship, okay, we got one equation. Okay, do you remember this? This is a relation for deriving the modulus of rigidity and the Young's modulus and the sigma. Okay, this video please go back and look into it, and we got a relation conducting the modulus of rigidity, Young's modulus and sigma when a body was sheared by an angle theta. Okay, so this equation I'm writing it straight away. Okay, you remember that we got this equation as eta in terms of alpha and beta. We got the equation as 1 by 2 into alpha plus beta. Okay, let's put this as equation number 3. Okay, 2 into alpha plus beta. Okay, and similarly, as we did here, if you divide the numerator and the denominator by alpha sigma on alpha on numerator and denominator, okay, this equation will get modified. This term is nothing but y. Okay, so y divided by 2 into, this will be 1 plus this will be sigma. Okay, so this equation I call it as 4. Okay, so we have equation 1 and 2. It's purely with respect to alpha and beta. Here equation 3 is with respect to alpha and beta. And but equation 2 and 4, there is no alpha and beta term. It is with respect to the Young's modulus and the Poisson's ratio. Young's modulus and the Poisson's ratio. Here it's negative, it is positive. Okay. So now I'm going to use this equation 1, 2, and 3, 4, and I'm going to connect it together. Okay. So write it down. So equation 1, this is going to be the equation 2. This is the equation 3, and this is the equation 4. Now, from relation 2, okay, I'm going to slightly modify this equation. Okay, I'm going to rearrange this equation 2 and 4 slightly. Okay, so can we write this equation as in terms of Young's modulus? Okay, so in terms of Young's modulus, I can write this equation as y is equal to multiply 3k into 1 minus sigma. Okay, so from equation 2, I'm getting this, and also from equation 4. Okay, let's put this as equation 4 is equal to, okay, 2 into eta into 1 plus sigma. Okay, this manipulation of these equations are very, very important. From one to another, you should be able to get. Okay, these are important for your understanding. Okay, how I'm getting from eta to y, y to eta. Okay, in the multiple choice question, sometimes this type of questions may be asked. So you need to be very clear how to get one equation from the other. Okay. Now, on the left hand side of these two equations, you are getting that y is the same. Okay. So shall I substitute this y value into this left hand side equation here? Okay, it's possible, isn't it? Y is equal to 3k 1 minus sigma. Y is also equal to 2 into eta into 1 plus sigma. So I'm putting I'm going to substitute this value of y onto this left hand side. Okay, so this equation I'm going to make it as, so since we know that, I'm writing this equation one more time. We know that y is equal to 3k into 1 minus sigma. This equation I'm writing it again on the top. And since y is also equal to 2 eta into 1 plus sigma, I'm going to substitute this value of y on the left hand side. Okay, so substituting for y on the left hand side equation. Okay, on the left hand side, okay, as y is equal to 2 eta 1 plus sigma. Okay, so this equation will become now, instead of y, I'm going to put it as 2 eta 1 plus sigma is equal to 3k into 1 minus sigma. Okay, now y is being equated on both the sides. Now from here, you need to find the value of sigma. Okay, you multiply 2 eta into 1, multiply 2 eta plus sigma, 3k into 1, 3k minus sigma, and then rearrange this equation. Okay, you will be able to get as, this is equation 1, let it be. If you rearrange this equation, okay, and you will find the value of sigma as, okay, directly we'll get the value of sigma from this equation as 3k minus 2 eta divided by 6k plus 2 eta. Okay, I'll write it on the top. From here, okay, from this equation, you will get, okay, the value of sigma be equal to 3k minus 2 eta divided by 6k plus 2 eta. Okay, just a rearrangement of this equation, multiplying and then rearranging and then calculating the value of sigma. Okay, what I have done here is, we brought the equation from the alpha and beta values to that of Young's modulus on both the sides, and then the Young's modulus values on both the sides are equated to one another, and from there we are trying to get value of sigma. Okay, sigma is common in both the terms. Okay, so sigma is now related with respect to the bulk modulus, with respect to the modulus of rigidity in this way. Okay, so this is an equation. Okay, this equation gives a value of sigma. What is sigma? Of sigma, which is the Poisson's ratio. Okay, which is a Poisson's ratio. Okay, which connects the bulk modulus and the modulus of rigidity. Okay, is that clear? So please memorize this equation. Okay, these questions may be asked sometimes in multiple choice questions very frequently. You should know how to get one from another. Okay, now sigma is known here. Now we will move on to the relationship which connects the y, k, and eta. Okay, now we got a term for sigma. Now we need to get a term for Young's modulus, bulk modulus, and the modulus of rigidity. These three. Okay, now sigma connects both the bulk modulus and the modulus of rigidity. Young's modulus is not here. Okay, so we need to get another equation which connects all the modulus of rigidity, say Young's modulus, modulus of rigidity, and the bulk modulus. Okay, so that is going to be the second part. Okay, so I'm going to now connect the relationship between the relation which connects all the modulus of rigidity, all the modulus of elasticity. All the modulus of elasticity. Okay. Say, what are the modulus of elasticity? Majorly it is Young's modulus, modulus of rigidity, and the bulk modulus. Okay. Okay. So these three we are going to find the relationship. Okay. So once again we need to come now to the equation. Okay. Let's, you know the equation 1, isn't it? So from equation 1 I'm directly writing from equation 1. Okay. We know that K is equal to what? K is equal to 1 by 3 into alpha minus beta. Okay. This is equation 1. Okay. And from equation 1, I'm going to say, from here we are going to take alpha now. Okay. The alpha. Find out alpha. Finding out for alpha. Okay. So I can take this one on the other side and rearrange. Okay. And then I'll have to write it as alpha minus 2 beta. Okay. Just alpha minus 2 beta is equal to 3K. Okay. Sorry, 1 by 3K. It's just 1 by 3K. I will put it as equation number 1 in a small way. Alpha minus 2 beta is equal to 1 by of 3K. I'm taking this on the other side. K, I'm bringing it on the other side. Now, let's move on to the same way from equation 3. Equation 2, no? From equation 3. Sorry, this way I will write it up from equation 3. Okay. What was our equation 3? It's with respect to modulus of rigidity, eta, isn't it? Eta is equal to 1 by 2 into alpha plus beta. Okay. Now take out this alpha plus beta separately. Okay. Here also I've separated alpha minus 2 beta. So I'm going to take this on the other side. So alpha plus beta is equal to, okay, is equal to 1 by 2 eta. I am bringing alpha and beta on the left hand side equally. This I will put it as equation number 2. Okay. Now I am going to add up these two equations on the left hand side and the right hand side. Okay. So see here, this is alpha minus of 2 beta, but alpha and beta are separated on both the sides. Okay. And K is on the other side. Eta is on the other side with this 3K on this 2 eta in the denominators. Now add up these two equations. So adding equation 1 and 2 on both the sides, left hand side and the right hand sides. Okay. Okay. Now you have equation 2, not adding first. You need to multiply equation 2. Multiplying equation 2 by a factor of 2. Okay. So multiplying, before we add, we need to multiply the equation 2 with a factor of 2. Okay. Because here it is 2 beta, isn't it? We need to get this also in terms of 2. That is why we are multiplying this factor with 2, with equation 2. Okay. So multiply this with 2, you will get 2 into alpha plus beta is equal to, okay, 1 by 2 and 2 will get cancelled, isn't it, on both the sides? 2 into 1 by 2 eta. Okay, so this and this will get cancelled and you will be left out with 2 alpha plus 2 beta is equal to 1 by beta. Now add up this equation with this equation. Okay, so you can put this as equation number 3 and now add up this equation. So shall I rub this one? So I'm going to rub these equations. Now there's a slight modification that we did it to bring this in form of 2 beta. So the 2 beta and 2 beta will get cancelled out. Okay. So equation 3, we derived it by multiplying equation 2 by a factor of multiplication value 2. Okay. So now add up these two equations. Adding up this equation 2 and 3, okay, you will get it as, this will become 3 alpha, isn't it, on the left hand side? Okay. This will become 3 alpha, and this 2 beta and 2 beta will get cancelled out, isn't it? I'll write it out. Alpha minus 2 beta is equal to 1 by 3. If you add up, this was our equation 1. Okay. Alpha minus 2 beta is equal to 1 by 3. This is our equation 1. I'm writing it here. Okay, so adding these two equations, adding the above two equation. Okay, so you will get this 2 get cancelled out, and this will become what? 3 alpha on the left hand side. So 3 alpha will be equal to 1 by eta, okay, divided by, so this will become 1 by eta plus 1 by 3k on the right hand side. Okay, so from here find out the value of alpha. Okay, so alpha will become, okay, if you take the multiplication factors, it will become 3k plus eta on the numerator divided by 3 into 3kn. Okay, 3k eta. So alpha value will become now, okay, so alpha value will become 3k plus eta divided by 9 into, okay, you may get this value of 3k plus eta by 9 into kn. Or this equation can also be rearranged, as, okay, in another form. Okay, if you take the inverse of this equation, okay, I will put it as 1 by alpha. Okay, in that case it will become, okay, 9k will go to the numerator, 9k. I'm just taking 1 by of this equation, 1 divided by alpha, 1 divided by this entire equation. So 9k will go to the numerator, 9k eta plus 3k by. Why we are bringing it in this form is, we have got a term with respect to the bulk modulus and modulus of rigidity and the Poisson's ratio, but we have not arrived at the Young's modulus. Okay, initially we started to derive the Young's modulus, bulk modulus, and the modulus of rigidity. But so far we are coming with two relationships with Poisson's ratio, but Young's modulus factor is not there. Okay, to bring it in the Young's modulus form, we are taking it 1 by alpha, because we know that 1 by Poisson's ratio is nothing but the Young's modulus on this side. Okay, so this will become 1 by alpha will now become what? The Young's modulus y. Okay, so y is equal to 9k eta divided by k plus eta. Okay, so this relation is connecting. Okay, is connecting all the three modulus of elasticity. Okay, on the left hand side you have the Young's modulus, on the right hand side you have bulk modulus, modulus of rigidity connected in this form of equation. Okay, so I will write it at the last here. Okay, so therefore the relation which connects, all the three factors, which connects all the elasticity, I can say modulus of elasticity is, all the modulus of elasticity is y. Okay, is connected to the bulk modulus k and eta as 9 times y into kn divided by 3k. Okay, 3k plus. Okay, this equation can also be modified. Okay, if you try to rearrange this equation, okay, this can also be slightly modified as another way of writing as, okay, if you just a rearrangement, if you bring this 9 and the k on the separate one, okay, just a rearrangement, if you try to do it, this can also be written as, okay, as 9 by, just bring the y on the other side, bring the other terms and rearrange the terms. This can also be written as 9 by y, okay, is equal to 3 by eta plus 1 by e. Okay, rearranging this equation. Rearranging this equation, you will get this form also. Okay, so both are same. If you cross multiply and do it, you will get back this equation. That's all. Okay. So this is a way of writing the relationship of the, now you see the numerator has some values, but the denominator has Young's modulus on the left hand side, Young's modulus connected to the bulk, modulus of rigidity and bulk modulus. In this way, 9 divided by Young's modulus value will be equivalent to 3 divided by the rigidity modulus value plus 1 divided by the bulk modulus equation. Okay, just the rearrangement, you will get this equation. Okay, so hope you are clear with this. This is a relationship which connects all the 3 modulus of elasticity. Say the Young's modulus, bulk modulus, and the modulus of rigidity. Okay, in this 3 way. Okay, so with this class is over, and also the significance of Poisson's ratio I would like to say here. Okay, you all know that Poisson's ratio is nothing but the ratio of the lateral strain beta, isn't it, divided by the linear strain sigma. One more time I will just write. What is sigma? Sigma is nothing but the lateral strain divided by linear strain. Okay, both are strain factors on the numerator and denominator, so it is, the dimension is same. Okay, so sigma has no unit, I can say, and the value of sigma ranges from -1 to 0.5. Okay, this is the value, -1 to -5 is the value of the Poisson's ratio. But for most of the material, okay, the Poisson's ratio value will be from sigma is equal to 0.2 to sigma is equal to 0.4. Keep this in mind. Okay, the value of Poisson's ratio for most of the material will range from 0.2 to 0.4. Okay, it can be maximum from the negative side minus to that of 0.5, but usually it lies on the positive side, not on the negative side. Very rare materials will have the value of minus, but otherwise the Poisson's ratio will always be between 0 to maximum of 0.5 or 0.4. So with this, I would like to conclude this class. Hope this is clear to you all. Okay, and I will end the session over here. Thank you for watching this video. I hope, I think